this episode, we are going to slow everything down and walk through network communication as if we are narrating traffic moving through a city. You have already heard about addressing, DNS, DHCP, TCP, UDP, and web handshakes. But memory does not become durable just because you heard something once. Spaced retrieval works by revisiting ideas in slightly different forms, forcing your brain to reconstruct the story rather than passively recognize it. So instead of introducing brand new concepts, we will replay the journey of a single device connecting to a website and highlight the essential checkpoints along the way. As we move through the story, I want you to picture each step happening in sequence, almost like watching packets travel on roads and pass through gates. The goal is not speed but clarity, because clarity is what allows you to reason about security when something goes wrong. Before we continue, a quick note. This audio course is a companion to our Course Companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at Cyber.Author.me in the Bare Metal Study Guide series. Start with the moment a device joins a network for the first time. The device does not yet know its own IP address, which means it cannot meaningfully send or receive normal traffic. To solve that, it reaches out using Dynamic Host Configuration Protocol, DHCP, which acts like a configuration service that assigns an address and other key settings. Picture this as a new driver arriving in a city without a map, asking a central office for directions and a temporary parking permit. The DHCP server responds with a lease, which includes not just an address, but also a default gateway and one or more DNS server addresses. That lease has a time limit, which ensures addresses can be reused when devices leave. Without this first exchange, the rest of the communication story cannot proceed smoothly. Once the device has an address, it can participate as a full citizen on the local network. It now knows its own identity and where to send traffic that needs to leave the local segment. This is where beginners sometimes blur the lines, so pause and ask yourself, what problem has been solved so far? The answer is local configuration, not name resolution and not application communication. The device still does not know how to turn a human-friendly website name into a numeric destination. That next step belongs to Domain Name System, DNS, which operates as a distributed directory. The device uses the DNS server address it learned from DHCP to ask a question about a domain name. Imagine typing a website into a browser and pressing enter. The device sends a DNS query that effectively asks for the IP address associated with that name. The local resolver might already have the answer cached, which speeds up the process, or it might need to query other servers in the DNS hierarchy. In either case, the outcome is the same. The device receives a numeric address that represents the destination. Notice how this step is purely about translation, not about transferring web content yet. If DNS fails, the device cannot find the destination even though it has a valid IP address of its own. Keeping that separation clear is crucial when you later analyze connectivity or security problems. With the destination address known, the device now prepares to start a transport conversation. At this stage, the question becomes which transport protocol will carry the application data. If the communication is typical web browsing, Transmission Control Protocol, TCP, is often used because it provides reliability and ordered delivery. TCP begins with a handshake, a short sequence where both sides confirm that they can communicate and agree on starting conditions. This handshake is not about content, but about creating a dependable channel. If you picture traffic lights coordinating cars before they enter a busy intersection, you are close to the idea. The handshake ensures that both ends are synchronized before meaningful data flows. During this TCP handshake, each side exchanges messages that establish sequence numbers and confirm bidirectional reachability. Once complete, the connection behaves like a managed stream of data rather than a series of disconnected packets. The sender tracks what has been transmitted, and the receiver acknowledges what has been received. If something goes missing, TCP retransmits it. This reliability comes at the cost of extra control traffic and slight delays, but it allows applications to behave as if the network is clean and orderly. For many applications, especially those involving web pages or file transfers, that reliability is worth the overhead. Now layer on the idea of security for web communication. If the site uses encryption, the device will perform a transport layer security (TLS) handshake after the TCP handshake is complete. This second handshake negotiates encryption parameters and allows the client to validate the server's identity through digital certificates. Think of it as checking identification and agreeing on a private language before discussing anything sensitive. Only after this step does the browser send Hypertext Transfer Protocol (HTTP) requests that ask for specific pages or resources. The visible web experience you see in your browser depends on these invisible setup stages working correctly. If the TLS handshake fails, you may see warnings about trust or security, even though the network path itself might be functional. Contrast that with User Datagram Protocol, UDP, which takes a lighter approach. UDP does not establish a connection with a formal handshake in the same way TCP does. Instead, it sends datagrams independently, without built-in acknowledgments or ordering guarantees. This design reduces overhead and can decrease latency, which is valuable for time-sensitive applications. However, it shifts responsibility to the application to handle lost or out-of-order messages. When you recall this difference, you should associate TCP with managed reliability and UDP with streamlined speed. Neither is automatically secure or insecure. They simply represent different trade-offs. As we continue the walkthrough, consider what happens when many such conversations occur at once. A single device might maintain multiple TCP connections to different servers, each identified by unique combinations of IP addresses and port numbers. Ports act as logical doors that allow traffic to reach the correct application on a device. This is how your browser, email client, and messaging app can all function simultaneously without confusion. From a monitoring perspective, these patterns create observable signals. Analysts can see which ports are used, how often handshakes succeed or fail, and whether traffic resembles normal application behavior. Now pause and retrieve the sequence from memory without looking back. A device joins a network and uses DHCP to receive an address and supporting information. It uses DNS to translate a domain name into an IP address. It establishes a transport conversation using TCP or UDP, depending on the application. If encryption is required, it negotiates TLS before exchanging HTTP or other application data. Each layer solves a specific problem and hands off to the next layer in an orderly way. That mental replay is exactly what spaced retrieval is designed to strengthen. Security reasoning depends on recognizing which layer might be failing or being abused. If traffic is misdirected, you might suspect DNS manipulation. If devices receive incorrect network settings, you might examine DHCP behavior. If connections are attempted but never fully established, you might look at handshake failures or filtering. By revisiting the communication story from start to finish, you build the habit of isolating problems logically rather than guessing. That discipline is essential when you later analyze intrusion techniques or design defensive controls. As a final reinforcement, picture the entire journey again as a flow of traffic through checkpoints. The device gets its license and directions from DHCP. It looks up an address in the directory through DNS. It coordinates entry into a conversation with a transport handshake using TCP or sends datagrams through UDP. It secures the channel with TLS if needed. Only then does it exchange meaningful application data like web pages. If you can narrate that sequence calmly and confidently, you have internalized the essentials of network communication. That internal map will serve you repeatedly as we move deeper into network security concepts, because every defense and every attack begins with the same basic act: two systems attempting to talk.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit BareMetalCyber.com.